Hello, this is Kurt Neubek. I'm an architect from Houston, Texas, USA, and we're here to talk about solar box cookers, a comprehensive analysis of design components. First, just a little bit about myself. As an architect, I studied solar architecture in graduate school in the 80s, and I've been back into designing solar cookers for more than 10 years. I've designed a wide variety of them and designed and built them, and I have also been doing a solar cooking demonstration at the annual Sandcastle competition in Galveston, Texas for the last 4 years to big crowds. Incidentally, those eagle-eyed among you might notice Luther Kruger on the lower right photo there. Now, the outline for today, for the next 28 minutes or so, is we'll talk about, first of all, fundamentals of solar box cookers. Then I did a series of experiments which I built and tested. I'll show you those. Then I did some computer modeling, and we'll show you a couple versions of those. And then finally close with some deeper analysis about reflections. So first of all, what is a box cooker? It's obvious it is a box. Always has to have a box, piece of glass, or some kind of plastic or something to contain the heat in, and you have a box cooker. Could be a simple box like the one shown on the lower left. I use that in cooking and demonstrating, proof some bread in there, for example, relatively low temperatures. But I also have on the right is an ugly hybrid box cooker. Commercial box cooker, and that will do, as you can see, about 160 degrees C. Use that for baking all kinds of things. But there are just countless variations. Now, a little bit more about, so how does box cooker work? There are inputs and outputs. As we said a minute ago, you get to the temperature based on how much gain can you pick up from the sun, and that's both direct through the glass as well as bouncing off of any reflectors, if there are reflectors. But you're also losing heat because even though there are reflectors, not all of the reflector is being used. Much or most of the reflector is actually just bouncing light away from the glass, from the box. You'll see that in a few minutes. So the design and the shape, that has to do with, again, that optical efficiency, the geometry, how much of it affects, how much of the light is actually getting in there. And then even the light that hits the glass, some of it bounces off. We'll talk about the Fresnel equations in a few minutes. And then there's just losses. Once some heat gets in there, into the box, there are losses through the outside of the box and through the glass as well. The other thing it's worth noting with any kind of a cooker is, let's say we have 1,000 watts per square meter coming in. It's a series of cumulative losses because there's only some percentage of the light hitting the reflector that's actually hits the glass, and even that only some percentage of that is bouncing off the reflector because some of it is absorbed. All of these things go into trying to determine how effective any given cooker is. Here's a table of properties of glass. And I'll just point out a few things on this table. The first three are so-called clear glass, single pane, double pane, triple pane glass. And so-called clear glass is actually slightly green and has iron in it. So then you can get what's called low iron glass. So that's single pane, double pane. And then finally we have a vacuum glass available here or visible here. And the data we have for each is the visible light transmission. You can see that, so for single pane glass, it's about almost 90%. But then when you get double pane, then that's that number squared. And then when you do triple pane, it's that number cubed, so it goes down. The amount of light goes down as you add more panes of glass. But the thermal resistance goes up, meaning insulation value of more panes of glass goes up. So the key is to try to find, depending on the configuration, when is more light transmission valuable. So for example, low iron, if you can get low iron, it gives just a little bit more light through it than so-called clear glass. And so percentage-wise, it's small, but it could be helpful for the same U value and R value. And then the vacuum glass has much lower light transmission, but a much, much higher resistance value. So it will retain the heat better. The lines cross. A little bit more about solar gain through glazing. They're known as the rad equation. Again, some of it of the incoming, some of it is reflected, some is absorbed, some is transmitted. And then depending on the angle of the light hitting the glass, here's the reflectance. As the incident angle goes up, the reflectance can go up dramatically, and therefore the amount transmitted drops off quite a bit after about 60 degrees. And so let me illustrate that. Here's a video of a piece of glass. I'll just lift it up. This is at my kitchen counter, looking at the backsplash. So I'll just lift it up, set it down. Now, if we look in the middle of the screen here, as I lift the glass, as we see, as the angle of we're looking changes, you start to see the reflection of the tile, and you start to get less of it is going through. Now I'll tilt it back down so you can see more. And as I continue to raise the glass, you see almost all reflecting. You're not seeing through the glass hardly at all. And the opposite is true. If we go down at low enough angle, the reflection of the mirror, of the counter, obscures the view of the tile. So that's I just want to illustrate for you what these graphs are and why factoring in the reflectance angle becomes important, so you don't lose that. Now, here's another way to think about it. Here's a diagram showing a cross section through a cooker. Here's the glass on the bottom, and if we put a reflector, let's say at 60 degrees tilt, then if you do all the math, the reflections come in here, they bounce off, hit the glass. This is what's called the incident angle. How the angle compared to perpendicular, that's the incident angle. So when the reflector is at 60, the incident angle is at 60, coincidentally. And so what I've done here is I did the math for you so that as the reflector tilt goes up, then as this tilt goes up, then you're good. But if you open it more than about 60 degrees, that's where you're going to start losing quite a bit. So that's a good rule of thumb. Now let's get into the tests of the box cookers that I built. I started with on the left. You can barely see. You'll see some of the close-ups in a few minutes of a sports locker, a 30-centimeter cube sports locker. Cut off one side, put glass on it, and then I made 4 different cookers where I varied the amount of insulation and then changed a series of other variables. So I'll show you some of the tests that I did there. The first day was no insulation. This was just really kind of an initial test to make sure that all the temperatures were about the same. You can see they were. I made sure that I was checking things like the performance of the cookers and just even my test procedure. And I also took this infrared photo. You can see it, not surprisingly, when the glass was aimed right at the sun with no load, all the light was going to the back of the cooker. So all the losses were through the back because that's what was heating up. So for the next test I did, I said, what if I just insulate the back of these where those losses are and not insulate the sides? What would that do? Well, this graph shows that the red is uninsulated. That was no insulation. That only achieved about 36 degrees. But the two in the middle with 5 centimeters of insulation performed about the same. And then the last one with double that performed slightly better. So no surprise there. Although these are not really hot enough to cook in yet. They're not quite cooking temperatures, but that was helpful. So then I did a series of additional tests where I started with these graniteware pots, 1 kilogram of water, and then a glass lid. And then I have these wireless temperature probes. And I have some wired probes too. You'll see some of those. But these wireless temperature probes actually have one sensor at the tip that suspends in the water, and another one at the end which measures the temperature of the air inside the box. So they're quite handy. So the first test I did, or this next test, was just of the 3 insulated cookers to see how they were performing. Slight differences there, as you might expect. The fourth time I did these tests, it was I had a lot of time, but you can see this is on the pyranometer in the middle here. It was very, very cloudy in the afternoon, so it wasn't a great test of the stagnation temperature. But the uninsulated, you can see what it did here. It ended up at about 39 C, and the two in the middle with the 5 centimeters of insulation ended up about almost exactly 58 degrees C. And the fourth one too, about 58. So these performed, the insulated ones performed about the same. And so at least at these temperatures, the insulation above the 5 centimeters really doesn't make much difference. So now by test 5, we'd added some reflectors, and these are 60 degree. So I built a 60 degree box here and put 30 centimeter square mirrors. These are silvered mirrors, so very highly reflective. And now look at the performance. The uninsulated is down just above 60 degrees C, 65 or so, 68 maybe. But the others, the insulated, are much, much higher. So they're well into the 90s. The two with 5 centimeter of insulation were these all performed nearly the same, but in the end, the extra insulation did help a little bit on this test. Here was the next day, or a different day, all the same parameters. This was double pane. I made sure all of these were double pane now, and got slightly different results this time, and I'm not sure what was causing that. And then here's another one where this is the better, I think, more predictable on the left. This is the uninsulated. You can see it hit 71 degrees C. Then the other three were all just about the same as far as hitting. They all hit nearly boiling. I never got them quite to boiling because these temperature probes can only go, they're made for meat, so the tip that goes into the water is limited to 100 C. So I got some errors, an alert that said you have to stop before it even hit the 100. But it was a successful test. And then the last one was too cloudy to really to get much data, but similar performance. The uninsulated was lowest, and the other three were about the same, with the thickest insulation performing just slightly better. So the intent here was to get enough data that I could form some kind of what does this tell me about predicting? And so my next step is to add an even larger reflector. I have these materials. I've started this, but I have not finished building or testing this. But I'll talk more in a few minutes why this shape. But I already have the materials to do that. Now, I also recognize that the downside to all these models of the physical testing is it takes a long time, subject to a lot of variables in the weather. And so then I thought, gosh, I wonder how much of this could I or should I be doing with the computer. So I spent a lot of time with various with AI, of artificial intelligence agents, to help me write various computer programs. We'll talk about 3 or 4 of them here today. This is what I call just a simple thermal model. I told the artificial intelligence, these are the variables I want to change, and please look at the best scientific data out there for solar box cookers and reference that, and to build a thermal model so that I can move these sliders and change these variables, and then we'll see what the temperature does. And through a series of iterations, I had to keep testing various things and giving it feedback until it got it right, and showed this little graph. And I thought, well, this is looking about right. This is somewhat predictable. So I can't guarantee it's perfect, but I asked it, what are the scientific references? It gave me a list of the formulas it's using and the scientific sources that it used. And so Duffy and Beckman and Funk and widely recognized sources for solar cooking formulas. So, And then did some tests, and if I move the sliders all the way down, so single glazed, minimal insulation, no reflectors, got about 38 degrees C. If they move them up to the middle, two double glazed, 50 millimeters of insulation and two reflectors, got about 88 stagnation temperature. And then if you move them all the way up to the highest available here, then I got to about 170 C. And of course, this was intentionally simplified. There are assumptions that it's a 4-hour test from 10 a.m. to 2 p.m. Dual axis tracker. It assumes that this is always looking directly at the sun, so that this amount of insolation is continuous. So I don't have to worry about, in this case, about latitude or longitude or cloudiness. But this is directly to start evaluating, well, when does double glaze matter? When does, for example, to play with these variables to see if I dial up the number of reflectors, does the double glazed or triple glazed, when does it help? When do those lines cross? So I also asked the AI, the artificial intelligence, to do a sensitivity analysis of that thermal model. And it did a series of the next series of slides. First is the insolation. Of course, as the amount of sun goes up, the temperature goes up. No surprise there. Box size, it insisted that very small. Of course, these are very small. 0.1 meters on a side is certainly very small. The box cookers that I designed and built were right in the middle there. And I was a little skeptical of this, and I kind of pushed the artificial intelligence. Why would that be? And it told me it has to do with the surface to volume ratio, and that's very well documented for solar box cooker studies. And so I thought, okay, well, that's something for me to look into another time. Glazing definitely helps. As I mentioned, it's possible that as you keep adding glazing, as I mentioned when we talked about glass, you're reducing the amount of incoming light, but you're increasing the thermal resistance. So at some point you get too many. So at least for double, triple glazing, according to this model, triple glazing would help. Insulation thickness, obviously insulation helps, but it helps the most when you get up to this roughly 50 millimeter that we were doing, that I did my test. Beyond that, it really only helps when the temperatures get higher, and my physical tests confirm that. The number of reflectors, of course, makes a big difference, and then the ambient temperature, of course, has an impact. Part of my premise for doing this is that I believe that even in very cold temperatures, even in cloudy conditions, or in the UK or places that don't get good sun, that with the right reflectors and insulation, that you can get a cooker to perform. Now, I also started with, before that model, a much more robust model. And in the end, it's not performing to my liking yet, but I thought I would go ahead and show you the progress I've made. So similar ideas, you can set the season, you can set the latitude, and it's reporting on the right here the solar components. So it's doing the analysis to show you what the azimuth and the altitude would be doing based on the latitude. And then also there's the box cooker dimensions. You can set the size of the box cooker, the reflector angle, the glass tilt here for the whole thing. You can set either to manual tracking or azimuth or dual axis tracking, manual or automatic. And then this shows the area of reflector that is bouncing onto the glass. And as you tilt the cooker, tilt the whole cooker in this case, then that also changes the total area and the ratio of the reflector area and the effective aperture area. And then of course there are the thermal properties of the box, the insulation and such, and the operating conditions, of course, how cloudy it is, and whether you're going to do water or glycerin or an empty stagnation test. I have those as variables. And then also I had to create a 3D model based on these variables. So as I change glass tilt, for example, then the model is also changing, not only in the data but in the 3D model, and the length of the reflectors also, you can see that as they change, that changes in the 3D model. Much of this I got working to my satisfaction. I was pleased with it, but as you'll see, the reason, by the way, all these graphs on the right were, I didn't trust the Thermob model. I didn't trust the assumptions. I didn't trust the calculations. So the solar components, the optical is working, the amount of reflector area, all of these things were working correctly. But then when I got into the actual heat flows and the temperature, this is the part that is not performing the way I expect it to. So this needs some more work with the cooker, but that's where I was going there. And then finally, the last piece of this is, some of you may recognize that a number of years ago, a gentleman named William Bradley from earthboundtech.com presented a paper and a presentation to what he called a reciprocal optical test. And what he said was, in order to study cookers, instead of trying to bounce the light from a sun to the cooker and trying to measure how much light hits the pot, what if we put the light in the pot and go back to where the sun is? This would be another way to study the reflectors and the effectiveness of the reflectors. So I had been modeling 3D in a computer, various designs, and looking, say, down the barrel at the reflections. I put a red ball in there just so I could see it. And I realized, gosh, this is the same as the reciprocal optical test, just by using the computer to do ray tracing. For these 3 different kind of cookers, as you see here, for example, that I had modeled, if I look down the barrel, I can see how much red, and by varying the shape and the configuration, I can add more red. I can add more of reflection that's going right onto the pot. And this one, you'll notice that led to these sort of cat ears, and you might say, well, why cat ears? And again, it just had to do with when I was looking at the reflections. And I later noticed that, gosh, a parabola, the cut off to a square and plan, gives you essentially those same cat ears. It makes sense why those reflections would work. Now, the next little test that I did was also used artificial intelligence to say, I want to create a little 2D study to evaluate reflectors. If we start with glass of, let's say, distance 1 here, and if you put a reflector of distance 1 on each side, so this is kind of the side view or cross section of the reflector, if you start with them wide open, then the light just bounces straight back. And if you go all the way up to 45 degrees, then the light will still bounce across the other reflector and go straight back up. It still hasn't hit the glass. You have to get above 45 degrees before it starts to hit the glass. And we get into those Fresnel losses that I mentioned earlier, those reflections off of there. So once you get up to about 60 degrees, now you have that optimal distance that we talked about earlier, where you get reflections. All the reflections from this are going into the glass, and very little losses. There are some very, very narrow, thin reflections there showing that reflected loss. Also notably, even at 60 degrees, if you make this longer than the length of the glass, longer than the length of 1, then everything above that just bounces right back up into the sky. So a larger reflector doesn't help. So if we bring that down back to the optimal at 60 degrees here, and we add another reflector, let's say also of length 1, then we can play with, well, what's that angle up here now to bring all of those reflections into the glass. And that turns out to be about, you can see 67, 68 degrees, something like that. If you study more of these and draw more, then you can pick a center point, and then you'll find that you've now created a parabola. So now I'm showing a pot in there and saying what would these do to get the light onto the pot. And if you wanted to study this to, say, get all the reflections, you go to the underside of the pot, because that's, since heat rises, if we wanted to get most of the light to go to the underside, that might lead you to a shape like that. Now finally, I did one more study in using some 3D software called Blender. Again, using artificial intelligence, wrote some software that uses some of the features in Blender. This little tab called Solar Cooker is something I created. The first thing it does is once you initialize the scene, it creates a default solar cooker here. And I can change a couple of parameters, and now there's a box, a cube with a red pot in the middle, and inside the reflections. And the thing that's most notable about why I used Blender is that this allows us to do real-time reflections. Now it looks more pixelated in the video than in the original, but the fact that it's recalculating those reflections as we move is frankly remarkable. It's very hard to do with normal computer graphics. So this was really interesting. So then I got to adding all the solar parameters, so I can set the latitude, the season. We can see what the path of the sun would be, and then we can get a sense that we can start thinking about what would the sun see, what would the views into this cooker look like from the sun's perspective. This goes back to that reciprocal optical test. So I added a feature to where I can say view this from the sun's position, hit this button. So now we're looking at, as I change the time of day here, this is the view of what the sun would see in this cooker. As I just drag the slider over, we can change the time of day and see what does this tell us. And in this case, it's a very simple box and with minimal reflections. It doesn't tell us too much. So now I picked the latitude of at the equator, at noon, at the equinox. So we know we're looking straight down on the cooker. And then I added this feature. Also, you can add reflectors. So here's the defaults to adding one layer of 4 reflectors. And you can see the variable angles. Now let's turn up the reflectivity just so we can see what's happening there. And notice that at 60 degrees, the far corners don't add that much. They add a little bit. But let me rotate this in 3D so you get a sense of what this is doing. So it just made those 4 trapezoidal reflectors there. And so now if we go back and look straight down the axis, so we have the sun's view, and this takes out the perspective and the parallax, gives you the orthographic view. And so notice if we have, there's the 60 degrees. If we turn that up to, let's say, 70 degrees, we see a little bit more, but now it's a slightly different angle, but now the reflector is basically too short. So let's turn that up a little bit, and we can see almost all of the pot. And you'll see the corners are much more valuable now at a slightly steeper angle. But what if we make this now an octagon? So I made this polygon so you can change the sides to nearly any number of sides that you want. And so now with 8, now we're seeing almost all red. My premise is that's what you really want. So the more sides, the more of a conical and more of a cone it is, the better. We want to say, what would it take to get nearly all red? So there's one where the first layer of reflectors is at 67, the second layer is at 72, and let's show you what the 3D view of this is. Now, one of the things you can tell is as the reflectors get longer, then you really have to have this on manual tracking, because otherwise you're going to be blocking more of the cooker than adding to it. And then finally, I added another feature that I called this film strip. If I take a start time, in this case 8 a.m., 9, 10, 11, 12, do a detailed rendering of each one, and then I thought maybe the software can do some of the analysis that was mentioned in the other analysis, to do pixel by pixel and figure out the area of the red, or the more red, or one direct or single reflection. And it's not working, I'm sure it's not really working purely yet, and even estimate the power or the wattage, but that's where I'm going with this study. That concludes my presentation on solar box cookers, comprehensive analysis of design components. I hope you found that of value. Thank you very much.